Alright, in today's lesson, let's look at functions. I know in past lessons I've probably slipped and already used that F word in math. Not that F word, but the function word. I do teach at Leverett Christian University, people. Quit laughing at me. But a function, what we mean mathematically when we say a function is the following. A function is a rule of correspondence. Just a rule of correspondence that that pairs every input value with exactly one output value. A function. One input yields one output. One thing goes in, one thing comes out. A couple other terminology before we look at examples. The set of inputs is called the domain of your function, and the set of outputs is called the range of your function. All sorts of functions in the real world, people and their social security number. For honest, non-government people, one person, one social security number. So, and vice versa on this one. If I go to the Social Security office and I give them a number, they'll type it in, and the computer should give them one person back. That is how Social Security numbers work. That would be a function. Possible not functions. Not a function would be, trying to think of one. Well, I mean, like if you have, I can't think of one that's funny. I'll be back. I'm back. What if someone, a person, the input is, a person, and their output is their address? Well, if that person's parents are divorced, he or she might have two different addresses. So it would just depend on the situation. But that would not be a function there, because one person would go in, but he or she would have to think or go, well, which one do you want? Do you want my mom's address? Do you want my dad's address? A function, there's no wishy-washiness. One thing goes in, one thing comes out. Mathematically, our notation for function notation is, we typically use f, parentheses, x, close parentheses, equal whatever your rule is. We use f because function starts with f. But you'll see g of x, you'll see h of x, because f, g, and h are all in the alphabet. If we were talking a business math class, we'd see r of x, c, revenue, cost, profit. If we typically use x for the input variable, but that doesn't have to be. We could use t if we were talking time. They're just labels, but The notation, it's going to be the name of your function, f, parentheses, your input value, and then you'll pair that up with your output value. For example, if f of x were x squared plus 4x minus 3, then we could plug in some value. Anytime you have the function notation, it's a function. Don't have to worry about it. So let's just pick some values and crank out the corresponding outputs. Like if we plug in 1, we'll get 1 squared plus 4 times 1 minus 3. So it'll be 1 plus 4 minus 3, which should be 2. So for this function, f evaluated at 1 is 2. You're going to have f parentheses a number all the time. You'll never just have f by itself equals a number. If we plug in 2, we'll get 2 squared plus 4 times 2 minus 3. So that's 4 plus 8 minus 3, which would give you 9. So we have f of 2 equals 9. These are all going to be points on the graph of the function. 1, 2 would be on its graph, 2, 9 would be on the graph of that function, so on. We plug in negative 3, just picking on a negative number. Then we get negative 3 squared plus 4 times negative 3 minus 3. So negative 3 squared is 9. Negative times a negative is a positive. Minus 12 minus 3 is going to get you negative 6. So f of negative 3 would equal negative 6. Okay? So, that's function notation. What we want to watch out for is that it's important that before we start plugging in values into our function, that we know the domain of the function, that we either consciously write it out or we subconsciously just look at it and know what values you can play with, what numbers you can't play with. So there are 2 ways to get kicked out of a domain. 2 ways to not be in the domain of a function. Number 1, cause division by 0. Number 2, even roots of negative numbers. Both of these will get you results that are not real numbers. For our functions in this class, we want a real number to go in and a real number to come out. I know that we have complex numbers, but we're not doing any complex number functions in this class. They're going to show up in the answers to our quadratics, but we're not going to graph complex functions. We want to deal with real number functions, which means a real number goes in and a real number comes out. So let's look at some examples and calculate the domain of the functions. So in that last function, I had f of x equals x squared plus 4x minus 3. Okay? Well, if we look at this function, analyze it, and we look at what causes you to not be in the domain of functions, division by 0 or the square root, 4th root, 6th root, the even roots of negative numbers, this function doesn't have either one of those problems. There's no division by the variable, there's no square root of the variable. So this domain this function will play with all real numbers. Any real number on the planet, you can plug it into x squared plus 4x minus 3, and then you'll get a real number back. If my function was 3x minus 2 divided by x minus 5, perfectly great looking fraction function. Okay, well, fraction right there, my radar goes up and says, hey, I bet I have a domain problem. There might be some number that this function can't play with. And there is, because x minus 5 is going to equal 0 when x is equal to 5. So if we try to plug 5 into this function, you're going to get division by 0. So the domain here is going to be all real numbers except x equal 5. Everything but 5 you can plug into this function and you'll get a real number back. Try to plug in 5, you don't get an answer back at all. You get undefined, because if you try to plug in 5, you get 3 times 5 minus 2 over 5 minus 5. So that's 15 minus 2 divided by 0. 13 over 0. We have no clue what that is because division by 0. If we had g of x equals 4 divided by x squared minus 9, and I wanted to calculate the domain of this function, then I want to look and see what makes that denominator, the bottom of that fraction, equal to 0. Well, it's a nice quadratic. We've solved quadratics in the past. And so we get x equals plus or minus the square root of 9, which is plus or minus 3. So the domain for this function would be all real numbers except plus or minus 3. X can't be plus or minus 3. Okay? If we have square roots, say f of t was the square root of 2t minus 7, a lovely function, but we want to talk about its domain, what numbers we can legally plug in, what numbers do we have to avoid. So if we look at the domain of this function, we have a square root. So in order for that square root to make sense, the number underneath, 2t minus 7, has got to be greater than or equal to 0. Because the moment it turns negative, we take the square root of a negative number, we no longer have a real number. We have a complex number. So the domain here is going to be everybody where 2t minus 7 is greater than or equal to greater than or equal to 0, which means 2t has got to be greater than or equal to 7, which means t has got to be greater than or equal to 7 halves. So our domain would be anything, all the values of t greater than or equal to 3.5. Before 3.5, this function doesn't exist. It has its birthday at 3.5, and then from there it has graph, and you can plug in numbers past 3.5. So before 3.5, this function doesn't talk to them. Okay. Let's do one other thing real quick in this section. You can plug in, let's go back to that opening example. F of x equals x squared plus 4x minus 3. Okay, so this domain, the domain of this function is all real numbers. I can plug in anything I want to my little heart's content. What you'll see if you go on into like pre-calculus or a calculus class, you'll see quite often that they want us to plug in really strange looking things like x plus h. This is a huge thing in math. So don't freak out. Breathe in through the nose, out through the mouth. Deep cleansing breaths. Okay? We did earlier, we could plug in any number we want to. Like if we plug in 5, we're going to get 5 squared plus 4 times 5 minus 3. Crank all that arithmetic out, and you get 25 plus 20 minus 3, which gets you 42. Okay? The exact same thing is going to take place here, but instead of having a single number, we have this lovely expression x plus h. So all we're going to do is up here in the original function's definition, the two places where we have x, we're simply going to replace it with our input value, x plus h. We did the exact same thing down here. We put in the 5s in the two places where x was in the original equation, and we had 5 over here. We'll do the same thing here, but instead of having a nice number 5, we have this lovely x plus h looking thing. So if we plug in x plus h, that's what it looks like. We typically want to clean this all up. So we'll FOIL this first one. X plus h quantity squared is x squared plus 2xh plus h squared. And then distribute the 4x plus 4h minus 3. And that's as good as it gets. There's none of those are like terms, so you can't combine them. But we would do something with them in a pre-calculus or a calculus class. We may do it here in college algebra, or I hate naming a class because I probably use this video in other classes, but I have, and I don't want to start over, and so I can't go back and edit this, so I made that mistake. But we would do something else with this inside another class, inside another problem. Okay? That's about it for functions. I mean, you'll have f of x equals your rule, and then you have f of some number equals a number, and I'm just making up numbers here on the summary page, which gives you a point on the graph. You will never ever, let's do it in red, never just have like f equals 5/3. Like divide this one by 3. That's not what we do. This notation, this is our input. This is our output. It's just a nice compact way of writing, telling a reader or telling yourself later, this is what our input was, this is what our output was. Okay? So you never ever will divide by that input to get f by itself. Never ever. Okay? Well, that's it for functions and their domains. That's a big deal. About their domains is what you can plug in, what you can't plug in to evaluate your function at. Talk to you later. Bye.